And I'll just request you if you can limit yourself within around 15 minutes.
Good afternoon, everyone. So I'm going to talk about the advanced traffic signal control system in Indian cities. So within this limited time, we will try to discuss on advanced traffic signal controllers, their relevance in the current scenario, different type of traffic signal solutions available across the globe, their applicability over on our roads, and the desirable features of advanced traffic signal controllers for Indian context. So before going into the advanced traffic signaling, let's see the current scenario of Indian traffic signals or Indian traffic junctions. So I would say most of them are pre-timed, that is fixed time. There are, it's easy to implement, low cost, and that works on some statistical data collected by a manual process. And we have few vehicle actuated signal controllers also on our roads. And this vehicle actuated signal controllers adjust the signal timing based on the real-time demand. And very few, or very, very few, adaptive traffic signal control system. So the adaptive traffic signal control systems, the real-time signal control is applied to a network of traffic junctions. So let's briefly see what all these things are. So the pre-timed traffic signal control system is pictorially represented in the slide. So this has no real-life interaction. Say a lot of signal programs are generated or developed based on the statistical information for a different time slot of a day and a different day of the week. And the signal control equipment, they simply look into this timetable and based on the time and day, so that is executed. So the result of this kind of system is this can cause unresolved queues, and probably we all might have experienced that the green signal is shown to a road where there's no traffic, and unresolved queues are there, and we are unnecessarily waiting on the other roads. So this is one major problem. But there is another advantage of this kind of signal controller that this can be coordinated very easily. So the coordination, signal coordination is a technique to reduce stop, delay, and improve travel time. So often we might have experienced that while driving on a corridor, so every other traffic junction we are getting a red. The moment we reach the signal, the green is lost and we are supposed to stop there. And we get a wait for the green, drive to the next junction, again we are getting a red. So this can be easily tackled using a method called, or technique called signal coordination. So this gives a progressive green signal at consecutive intersections when traveled at a specified speed. So that's a constraint when traveling at a specified speed or a design speed. And most of us might have heard of the signal coordination, but a lot of myth is thought about the signal coordination also. That is, the first thing is, we take a number of junctions in a corridor and try to coordinate them. So any type of junctions can be coordinated. That is a general thinking. But it's not like that. So it has got a constraint on the cycle length. That is, how much time is required to serve all the 4 roads if it's a 4-arm junction. So we can bring the junctions to a coordinated group of controllers only if they are having similar traffic characteristics, or they should agree on the same cycle length. Then only that can be brought under a coordinated group of signals. Another myth about the signal coordination is that if the signal coordination is enabled, so all the vehicles getting the green in the first junction, they can go through the entire traffic junctions without interruption. That also is not true. Because another constraint in implementing that one is that ground speed. So there is a design speed, and there is a practical speed also. The practical speed varies depending on the congestion, because the speed is a function of the density of the traffic. So that varies. So at the most, we can expect 70 to 80% of vehicles getting the synchronized signal while traveling on a corridor. And another thing, people expect that so it can be synchronized in all the direction. That also is not possible practically. So generally, while selecting the synchronization plan or adapting the signal synchronization, the direction of maximum flow is identified and coordination is applied to that junction. That is, we have very clear morning peak, evening peak. So in morning peak, it will be coordinated in one direction, and evening peak, it will be in another direction. So this is how it is implemented. So there is one constraint into this. There should be a common cycle time for all the junctions in the coordinated group. Now we come to the vehicle actuated signal controller. That's another type of advanced controller we are having. So the vehicle actuated signal controllers use vehicle detectors to assess the real-time traffic demand on the road and accordingly modify the signal timings. So there is a real-life interaction. So the traffic data is collected like vehicle volume count, average detector occupancy, speed, average vehicle length, and that kind of thing. And the vehicle actuation signal can be vehicle actuated, but it requires at least 10 parameters if you are applying an analytical method. And it is possible to have some heuristic methods where it can be realized with a lesser number of parameters, input parameters. For the vehicle actuated signal controller, we want to assess the real-time traffic scenario. And for that, we are using some electronics or some others. And there are n number of different vehicle detectors available, starting from the inductive loop, which was the most popular one. And the inductive loop is just putting across each lane, a wire loop is kept. And when a vehicle intercepts that wire loop, the change in the inductance is measured or identified by the electronics connected to it. And that identifies that's demand or that's a vehicle. It's cheap. It's difficult to implement because it's intrusive. We need to cut the roads and put it and seal it. And it's easy to get damaged also. And then the camera-based system came. So some video analytics is used, and that identifies the motion detection. And the photograph, I don't have a pointer, in that second one on the bottom, you can see that the cars, and on the top you will find that the physical loop, which is a photograph from Bal Gandharv in Pune. And the bottom one is a photograph from Trivandrum. So the camera, the virtual loops are marked. The virtual loop in the direction zones are marked. And whenever the vehicle is crossing the direction loop, so it is identified. You can see that black and white color for that different loops. And radar type is there. Microwave radar is used. And thermal cameras, piezoelectric, magnetic, IR, and a number of things are there. And all these detectors are having its own strength and weaknesses. So the inductive loops are all weather, so it can detect the vehicles in all time, all weather, whether it's night or day. There is absolutely no problem. But the camera has got problems during heavy fog, heavy rains, low light condition. So while selecting this kind of vehicle detection, we need to have a feel of what kind of weather is going to happen in that city. And the microwave radars, it is cheaper compared to the camera, and it is all weather, but it has a problem that, so we cannot have the smaller sections or smaller detection zone identified that can look into one approach. If it's a road-by-road clearance or it's a BRT corridor, the microwave radar is recommended for that. And the thermal cameras are better, and they are being introduced to the industry recently. Previously, they were very expensive, and the price also has come down now. And the piezoelectric and magnetic, they are not widely used. Now we'll come to the advanced traffic signal control system. So we had discussed about the pre-timed controller, which is the first generation, and the vehicle actuated signal controller. But the vehicle actuated signal controller, since it is the signal timing are varying with respect to the traffic demand, so it does not have a fixed cycle length. So that's a constraint in providing a coordinated signal control under the vehicle actuation. So there are some special treatments required for that one. Now, these are good at isolated intersection. But in any city, there are n number of junctions and n number of corridors. So we need to think in totality of the traffic network. So the advanced traffic signal control system provides real-time signal coordination of a group of traffic signals based on real-time traffic demand. So this is a real-time signal coordination applied on a vehicle-actuated scenario, vehicle-actuated platform. So the vehicle-actuated platform can be just collection of the vehicle data and processing it at backend and applying it to the network of traffic junctions in real time. So it operates in two levels. So we have the local level at the traffic signal controller and other field equipment, and in the central level, an ATCS application software running on a computer. So both levels are networked on a robust communication backbone. So the local level controller will collect the traffic data and send it to the central controller, and the central controller process it and see the optimum, it derives the optimum signal timing and send it back to the local controller for execution. This happens in real time. And another advantage of this kind of networking is that it generates decision support reports and logs. Because since the vehicle detection data is available and it is being sent to the central computer knows what is the demand in each and every junction, and it knows what is the signal timing required for each and every approach of a road. So if this is properly analyzed by a traffic planner, like a processor car or someone else, then it is easy to identify the congestion cycles, and that is a vital information for the planning for the town planners, and of course for the police also, because they know that which junction is going to be congested during what period and what is the kind of manpower they need to deploy there. So now what is happening is, most of the decisions, or 99% of the decisions are based on perception. I say that, the junction is congested. How much congested? And is there a scope of improvement? So some data is required, and this advanced traffic signal controllers provide that information. And it supports remote monitoring and administration also. Because since it is connected through a network with a central computer, it is possible to provide VIP, green waves, and switch off the junctions from the center control, or to put it in the flash mode. So this is pictorially represented here. So n number of traffic signal controllers or the field equipments can be connected to a center level control. So maybe there are 1,000 junctions in a city like Delhi. So it is possible to bring all the 1,000 junctions to a central common control and monitor and manage it from the center computer. So the ATCS also can be in different flavors. That is the traffic responsive system and the adaptive signal control system. So the traffic responsive system selects an appropriate signal plan selected from a library of coordinated signal plans and based on the real-time traffic demand. So if you look closely, this is more or less similar to the pre-time signal controller, where we are having a set of timetable, and based on the time, the signal plans are selected and executed. Now, the timetable is replaced by a real-time scenario. So the situation is identified and verified by the signaling system, the adaptive signal or the traffic responsive signal control, and an appropriate signal plan is selected and executed.
Mr. Ravi Kumar, just try to
sir.
quick.
Sure. So the adaptive signal control, this is a real-time system that collects the traffic data and generate the signal timing and appropriately coordinate it real-time. So there are at least a dozen different operational models available across the world on the adaptive signal controller, starting from ACS Lite, Balance, InSync, LATCS, Motion, OPAC, Roads, CAT, Scoot, Autopia, and Cost. So this can be again classified into based on their action, that is either reactive or proactive, or proactive and reactive. And this can be model-based or non-model-based. So if you look closely into that this table, we'll see that ACS Lite, CATs, and Cost are non-model based. The ACS Lite is the latest addition to the family of ATCS, and is sponsored by the Scoot people. And SCATs and Cost are purely reactive type, and the Cost is an Indian version of the adaptive signal controller. All other adaptive traffic signal controllers are developed in developed countries. So it is again model-based and non-model-based. See, the model-based depends on some microscopic, mesoscopic, or microscopic models. And the non-model-based, they based on functional relationship between parameters that describe the change of traffic conditions. And the ATCS also, there are a lot of myths, like an ATCS solves all urban traffic problems. In reality, it is not like that. It increases lane carrying capacity and travel speeds, reduce delays and stops. And all the ATCS are not doing optimization on all the signal time parameters. So some of them do some optimization, and some use heuristics, and some use a relational basis. So a network or a network called traffic junction is divided into smaller area, and the smaller areas are separately synchronized. So if you look at, we are having 3 models tried in India. So Scoot was tried in Delhi, Ithaca is being used in Mumbai, and Cost is used in Jaipur. Scoot is not operational right now, but Ithaca and Cost are running. And this Cost was tried in Pune also, so it was working till last December, I remember, and after that some administrative issue, it's not there. And so if you look at what is suitable for our country, we are having this non-lane based driving, that is, the lane change can happen after the stop line, and the one detection, on the left-hand side, you will find the loops. One car is intercepting 2 loops, or one loop is intercepted by 2 cars. So taking the volume counts, turning proportion, headways, gaps, all those things are difficult. And if it is a mixed traffic flow condition, again, collecting parameters are very, very difficult. And the calibration is very much complicated in analytical models. We need to have n number of parameters taken, and a lot of assumptions are also there. Emmanuel, this is from the Telvent side, Telvent Adaptive Signal Control, which is used in Mumbai. So we need to know at least 7 to 10 seconds before the vehicle reaching the stop line, the volume count. So that is, but in our roads, the stop, and the assumption is that there is no lane change happening within that 100 meters or 120 meters. But in our case, the lane change happens after the stop line even. So what is required is, handle non-line based mixed traffic flow condition, and implementation of complex phasing schemes, self-calibration of phases and cycle lengths, and dynamic route selection, real-time signal coordination, fallback operation in vehicle actuated mode, remote monitoring and administration, and scalability also. Because in our case, implementation funds are coming in piecemeal. So whenever there's some funds, you should be able to expand it. And decision support reports and local expertise is very much important. And there should be a simulator interface also. And the relevance of the topic is the adaptive traffic control system is one of the major components of all the smart city mission projects coming up. So we need to critically look at what we are going to implement and what we are going to procure for our roads. Thank you very much.